Welcome to solverfy.
In this problem, we have light shining through three separate materials, each with a different index of refraction, n1, n2, and n3. We can see in their diagram that there are two different paths the light can take in order to transmit into the third material. And because these paths have different lengths, in general, the two transmitted rays will be phase shifted one from the other. And they want us to find what thickness L of the middle material will result in minimum intensity of the transmitted light, which means that these two rays come out half a wavelength out of phase. The information they give us is that the indices of refraction are n1 is equal to 1.5, n2 is equal to 1.34, and n3 is equal to 1.42. We're also told that the vacuum wavelength of the light, lambda, is 587 nanometers. So the extra different distance traveled by this reflecting ray here, which is labeled R4, is going to be twice this thickness L. So that's 2L, and that's got to be some half multiple of the wavelength. So we can write that as lambda times, well, actually it's not lambda because this is the vacuum wavelength, and this light here is traveling in some material. So the wavelength in the material is the vacuum wavelength divided by the index of refraction. So that's n2. Oops. n2. And we want some half multiple of this. So that's going to be m, which we'll say is some integer minus 1/2. We're almost done here. We just have to check for any other phase shifts. Because when you're at a surface here, as light goes from a lower index of refraction to a higher index of refraction, the reflected ray will be phase shifted by half a wavelength. So when we go from n2 to n3, we're going from lower index of refraction to a higher index of refraction, 1.34 to 1.42. So that means this reflected ray gets shifted by half a wavelength. So now this whole equation is off by half a wavelength. At this surface here, when we're going from n2 to n1, we're also going from a lower index of refraction to a higher index of refraction. So we shift again by half a wavelength, which means the total shift is a full wavelength. So we're back to no shift at all. Right, if you shift by a full wavelength, it's the same as not doing anything as far as the phase shift is concerned. So now this equation we know is correct, and we just have to solve for L. But you can see there's m here is some integer, and it can be any integer, so there's multiple thicknesses that will satisfy this, and they want us to find the second smallest thickness. So second smallest thickness means that m here is equal to 2, right? Because the smallest will be m equals 1. So we have m equals 2, this is an m, and so we can just solve for L here. So we divide by 2, so that can be lambda over 2 and 2, and then times m minus 1/2, which is 2 minus 1/2, which is 3/2. And plugging all the numbers up here, this turns out to 329 nanometers.